Welcome! You're about to listen to a presentation by Professor Dr. Oguz Celik, a professor of structural and earthquake engineering at the Istanbul Technical University and associate editor of the Journal of Steel Structures. The presentation of Oguz Celik was part of the program of the third panel organized by Çare as part of the panel series Turkey and Syria after the earthquakes. Professor Celik studied civil engineering and holds a master's and PhD degree in structural engineering at the Istanbul Technical University. His postdoctorate research brought him to New York, where he worked at the SUNY Multidisciplinary Center for the Earthquake Engineering Research. Professor Celik has both research and application experience in seismic assessment and retrofit of existing buildings, both new and historic. He visited earthquake-stricken areas in Turkey and Italy, and he participates in speaker engagements all over the world on the topic. Professor Celik's current research focuses on the analysis, design, and development of seismic energy dissipation members that could be used in new and seismically vulnerable structures.
Please welcome Professor Celik.
Okay, hello everyone. It's a pleasure to be here, and thanks for the introduction, Nizam. This is actually my talk is a little bit long, but I will be wrapping up very quickly. Could I ask this? Okay, this is the title of the talk. I will be talking about the aftermath. Aftermath means here 8 months after what we had. I will be starting with the damage assessment, actually talking on what went wrong really, and how are we going to fix them, right? And I would like to thank all the organizers here, and especially for inviting me to deliver this talk. So here we start with Gölbaşı. I'm going to talk about a little bit on the building behavior, especially on soft soil. This is an area where we experienced a lot of liquefaction failures. I will be showing you some images from the area. I spent a lot of time on that area after the February. So we will be starting with the seismic hazard map of the European countries, including Turkey, and the area affected from these earthquakes given in the Turkish part, as you see here with the blue circle. So we see that we expect quite large accelerations in around Turkey. As you see here, we expect larger than 0.5 G or more accelerations in the area, together with some other southern European countries, as well as Italy and so forth. So also there's a very serious region in Romania, for example, in the Rancha area. That area is very critical too. So if we get closer to the Turkey map, so you see that we finally currently experienced an earthquake in especially about 500 years return period. This is called as the rare earthquake, probably very rare earthquake. If you go back to the previous earthquakes in the past, you will see that those earthquakes or similar earthquakes happened in the area quite similar to those magnitudes shown here. So the region is quite problematic in terms of the seismic hazard. So in the past, in 2020, this map also shows you as a seismic hazard map. The current seismic hazard map shows you the earthquake in Izmir area. That earthquake actually happened in Samos Island of Greece, but affected Izmir city and resulted in about 20 building collapses in city and killed many people there. And also the people around here in Istanbul, for example, are expecting the next big one in near future. Some seismologists say that that big one is overdue, or some say that, okay, we have some 20 or 30 years more, but the magnitude is quite large. our building stock in this area is too weak to withstand such a big earthquake, measuring 7.3 or 7.5. So again, coming back to the Kahramanmaraş area, this is a list of devastating earthquakes in Turkey in the last 31 years. I made a lot of reconnaissance investigations in Turkey and abroad, especially in Italy, earthquakes. So we basically, I'm leading a team at ITU in my university to organize some one-day only events, focusing on several topics of earthquake engineering and before earthquakes, not after earthquakes. This is quite usual, talking about earthquakes after the earthquake, but to prepare people and to explain the problems. Also, we are talking about historic structures, for example, in seismic areas, as we had problems here in Hatay or Antakya, especially for the heritage building. So the latest earthquakes had incredible, huge, magnitudes. Seismologists say that they calculate the magnitude 7.8, 7.9. There are some differences on that. But sometimes if you take into account some other parameters, they say, okay, it's 8.0 magnitude. This is huge. The older and old, or I would say substandard building stock or heritage buildings were quite weak to withstand such a big earthquake. And unfortunately, on the same day, we had the second big earthquake, 7.7. Again, so during the first earthquake, the buildings were weakened significantly. Some collapsed, of course, but the weakened ones, unfortunately, collapsed in the second one. So this is a very simple map showing you some acceleration stations in the region. We picked some very significant ones, and we obtained the acceleration displacement response spectra. Okay, I understand that most of the audience is architects, but these are some engineering parameters, and we use them to evaluate the damage to performance of buildings during earthquakes. Very helpful also in the performance-based design of the buildings in the area. Also, we looked at the acceleration response spectra of some from elastic to inelastic or damaging buildings, and we saw that finally the buildings that type of damage and collapses could be explained by the acceleration data and the diagrams obtained from this data. So again, this is a list of, I'm not going to, because I have a very limited time, so I'm not going through all the items, but there are very serious reasons for this type of huge damage in the area. For reinforced concrete buildings, for example, starting from poor material properties for both concrete and steel. And there were also many architectural-based structural damages, basically defined as the irregular structural systems in plan layout and elevation. Those are really well defined in the current seismic code of Turkey. By the way, the code is very strong, and I'm in the code writing committee of this code. These irregularities contributed to damage or collapses in the area in the aging problematic building stock, unfortunately. And there's a very special thing here, pounding or hitting buildings. There were some hammering effects in the buildings in series. We observed this time a lot of damage or collapses from these stuff. So short or captive columns or some others, plus non-ductile structural systems, elements, very flexible concrete buildings, they all contributed to the damage. The last but not the least, of course, the local soil effects played an important role, especially in the area where we observed a lot of damage. So they magnified or amplified the soil effects during the earthquake. This is the diagram actually shows a very, very important response spectra curves obtained using the acceleration data. We saw that the bottom line here is these earthquakes, this is the first earthquake, these earthquakes resulted in some demands in the structures, almost all kind of structures in excess of the current code values. This is a very interesting topic to be discussed probably in the triple B Building Back Better phase of this after the earthquake. Okay, so the similar damage typology could be given in especially for timber or masonry structural systems, poor material, irregular systems, again, local soil conditions, and some large wall and floor opening sizes as well. So there are some methods to talk about some parameters affecting the building performance. One is increasing damping is quite useful for structural systems, or elongation of the building period is sometimes useful, especially when you're using a isolation system. But when retrofitting, you add some additional structural elements, and then they are shortening the period and attracting more structural forces in this system. Also, increasing ductility comes with a cost. That cost is actually damage that I will be talking about in a minute. Anyway, so what we know is we know almost everything. We know how to design a structural system earthquake safe, but the problem is the implementation in the construction site. This is a map. This is a very important map, by the way, taking into account the heavily damaged or collapsed buildings just after the earthquake. Tens of thousands of buildings have been scanned here, and we saw that finally that the damaged areas follow the faulting mechanism in the area. Okay, so the very interesting problem is buildings in series, and sometimes if you have a separated buildings, this is quite nice, but when they are attaching or touching each other, which is not so good, where we observe everything almost around here, even in Istanbul. But even your buildings are separated. If your neighboring building is not a well-designed building, and whether even your building survived a quake with some minor damage, but if the next building is overturning and hitting your building and damaging your building, so this is what we need to, talk about. Resilient of your building could be fine, but resilient of the city is a problematic thing actually. So it's a very critical thing to have a resilient city, not only your building, I would say. Okay, so this is a pounding effect, is very serious, especially when you have two buildings with different story levels, and they are hitting each other and breaking their columns. One of the most important problems is the rotational or twisting effects or torsional effects of the buildings, and we saw many buildings like this. The major question was if retrofitting were working. I would say yes. So this is a building just retrofitted prior to the earthquake. This is, I believe, this is Hampton Inn by Hilton. So they, according to their procedures, so a building should be earthquake resistant or so forth. So they retrofitted to that building prior to the earthquake, and this is one of the strong building, surviving building in the town of Kahramanmaraş. So, and of course, if a retrofit is done appropriately, it works. There's no problem with that. On the other hand, there are some other mid-rise or high-rise buildings, mid-rise to high-rise buildings up to 15 stories, and they experience a lot of damage and some collapse. School buildings are very important, and as you see here, there's a missing story here. That story was cut, failed during the earthquake due to many reasons that I listed before. Okay, this is a pancake type of structural collapse, and there are some other collapses, basically from soft stories, weak stories. There are many reasons, from irregularities, non-ductile detailing. There are a lot of buildings here, even in Istanbul, or this building typology is almost more or less the same in every part of Turkey, including Istanbul. So my concern is we have a similar building stock, aging building stock, and they have the similar problems. So if another earthquake, strong earthquake happens around here, and probably the scenario damaging or the collapse scenario would be quite similar to that. So this is a very interesting collapse mechanism that we call it the short column or captive column. This is an architectural based design problem resulting in many big problems, especially in that shortened column under cyclic laws during the earthquake forces. We have bar fractures, spalt concrete, crushed concrete, everything, right? This is another school building collapse that was an addition to a building, but unfortunately that part collapsed very badly. So there's a big dilemma actually. High damage design, we usually follow a sort of a level of, our buildings should be designed to allow a level of damage accepted. So a high damage design or low damage design or damage avoidance design or no damage design. So we should be talking in the triple B, building back better, okay? So I'll be wrapping up very shortly. So this is a seismically isolated building. It's a hospital building in the area, and we see that although it's under construction some part, but the other part was already completed. So the structural system elements, they are looking very good. Prefabricated buildings, they are using very high quality of concrete. There's no problem with that, but their structural system or the connection details were weak enough to cause such collapses in the area. We had also some steel buildings around and also some other tunnel form concrete buildings around. They performed very well, by the way, but some non-engineered even still, they failed very badly. Of course, heritage buildings are really critical in Antakya, Hatay area. They suffered a lot of damage during the earthquake. These are mosque damages from the area. Again, especially the dome damage, huge, very heavy dome damaging the building. This is, again, from Hatay, Antakya Protestant Church. So there are some images here from prior to the earthquake, and this is the top part of the building collapsed very badly, unfortunately, right? So this is the Orthodox Church, again, before and after the quake. And there are also some buildings that were not damaged during the earthquake. There were some reasons for that, including the soil properties as well as the structural properties. This is a building mosque in New Mosque. This is from Malatya, damaged in the 2020 earthquake, but collapsed in this earthquake as well. This is a minaret collapse. And this is a governor building in Malatya. This is basically a hybrid system with concrete as well as solid brick system, but there were some partial collapses, but it was okay. I mean, the building was up. An out-of-plane damage to buildings, masonry buildings, as shown here. So the short column is bad. Strong beam, weak column is bad, so you have to retrofit it. Strong column, weak beam is nice, as you see. Buildings usually constructed before 2000, they follow the first one, which is bad. They should be retrofitted after 2000. So we have quite nice buildings actually in Turkey. And in the retrofit process, so you have to eliminate irregularities. This should be your first preference. Okay, I'm not going into details, but you can add some shear walls, you can add some X braces if you want to use steel braces, or for pounding buildings, there's no practical way to minimize pounding, but you should increase the lateral stiffness in those areas, okay? Also, if necessary, you have to follow some soil improvement methods in the area, or especially for the building owners, external retrofitting is very useful by using braces or dampers. These are examples from Tokyo, and we follow in Turkey too, similar examples. So without evacuation of the building owners, this is a good alternative. So, okay, the number of buildings in Istanbul, these are some numbers, 65% buildings are with 1 to 4 stories, and almost, let's say, 70% of the buildings before 2000 or 1980s to 2000 buildings in Istanbul. Okay, so that means we have a really big problem in Istanbul as well as in other parts of the country. So 82% is reinforced concrete. So these are all, I would say, mostly vulnerable to seismic actions, and some others are also listed here. So the finally, we're finishing Istanbul. There are a lot of retrofit works here undergoing. So the Minister of Education sent a letter to all building school owners that their buildings should be ready for the next big one within months. I mean, so they started to retrofit their buildings with some conventional methods, some advanced methods, whatever they want. And for the reconstruction, this is the last one, around 6,000 residential units are needed, and around 200,000 units per year is planned. And the idea is to have earthquake-resistant, fast, cost-effective solutions. So, of course, aesthetics is very important. Two, alternative systems for low-rise, mid-rise buildings are sought for the new construction. 1 to 2-story residential buildings are planned. 2 to 3-story residential buildings are planned. There are some RC dual frame or shear wall systems or tunnel form systems, especially. The government wants to encourage this because their performance was really good during the earthquake. And I just would like to attract your attention to other structural systems like steel framed or dual braced or regular systems, or lightweight or cold formed steel systems, or industrialized or modular panel systems. These are very important too. Or we should be looking at some robot-aided, accelerated building apartment units. This is very important. Chinese people, they do that very, very quickly. So the number of buildings is huge, and the time is very limited. So I hope we do that triple B in a good way. I'm actually personally optimistic about that. I'm not that much pessimistic, but there are very difficulties to be solved within the next months. Thank you. This is Istanbul, a nice view, probably a nice or bad view, I don't know, but we are expecting the next big one in future. The population is about 16 million. Thank you. This is an announcement. There's an American Society of Civil Engineers Journal of Civil Engineering journal led by Professor Ertuğrul, as he will be talking in a minute. So there's a special collection of this February Turkey earthquakes, and he will be leading the group, and I will be taking as the one of the guest editors in this journal. Thank you.